Hello, I'm Ian Stewart. I'm currently titled the Supervising Geotechnical Scientist Strategic Capability and Risk, and I work in the geotechnical science area of the Pavements and Geotechnical Engineering branch. This presentation is about compaction, one of the basic processes that we use in our roadworks construction. It applies to both earthworks and flexible pavement materials. And we'll be talking today about the principles involved and the way to find best practice for your particular materials and your particular project. Now, firstly, what is compaction? Word we use often. There are many definitions around. I'm sure you'll have seen some of them in the basic textbooks you use or in your training at various times in your career. The one I've chosen to adopt is a recent one from an Australian Standards Soils Testing Handbook. It was published about 2 years ago, and it says, compaction of a soil is the process by which the soil particles are packed together more closely using mechanical means to reduce the air voids in the soil without reducing the moisture content. Now, we'll be unpacking that progressively as we go through this presentation and trying to draw out some of the practical implications. Firstly, why do we bother? There are a number of different reasons. Firstly, we're looking at the soil materials having sufficient strength to support, firstly, their own weight, what we call the self-weight, and also live loads or fixed loads from traffic and from structures, which may be supported by it. Obviously, in our case, traffic is always there. Structures may or may not be. That can include things like bridge abutments, it can include noise walls, many other things. Signposting is another. We're also looking for what I've called dimensional stability. That relates to two things. Firstly, the internal settlement of embankments under their own weight. As that weight under the force of gravity reduces the void content. And secondly, we're looking at the effects of dynamic loads from traffic, both the loading and unloading cycle from passing vehicles, and also the thumps and bumps that you inevitably get from passing traffic on an uneven surface. And the sad reality is that all road surfaces become uneven in the long term. And what we're really asking for is that the levels and dimensions of the road surface stay where they are and aren't affected adversely by changes in the volume of the embankment. And lastly, particularly for pavements, we're looking at control of permeability. That is the ability of water to get into the materials and reduce their strength. Obviously, the more compaction you've got, the less permeable the material will be. Now, how do we get there? Again, there's a very simple answer, almost in one word. We get out one or more of these. Now that, I guess, is obvious. But how does it actually function? And to work that out, we need to have a bit of a look at what we're actually working with. Now, for our purposes, everything we compact is referred to as a soil. Now, the way we use it, that term in engineering, is a little different to the way it would be used in common speech. So it covers not only what we normally think of as soils, it covers weathered rocks, covers crushed rocks, even covers rock fill. It covers a great variety of things. Now, we normally think of it in terms of size ranges. Soils can range from gravel, including cobbles and boulders, which can go up to many hundreds of millimetres in size, metres in fact. And that size fraction is generally made of rock fragments. There's very little else in it. Beneath that, we have sand, again, everyone will be familiar with, from beaches, from any sort of concrete work you've done, you'll have seen some sand. Various other applications, and that's in a size range from 2.36 millimetres in Australian usage down to 0.06 of a millimetre. Now that's about the width of a human hair, and it's the smallest thing you can actually see with the naked eye in most cases. Depends a bit on the quality of your eyesight, but generally that's about it. And sand is composed of both mineral grains and small rock fragments. Below that we have silt, which runs down to a few thousandths of a millimetre in size, down to the point actually where you can't see the individual grains even with a good microscope. And that's made almost entirely of fragments of mineral grains or individual grains, other than clay. Clay is even smaller than that, down to well below microscopic size. Now, to give you an idea of the relative size ranges, we've got a small illustration, which you can see here. The big one is about the biggest size of sand grain, a couple of millimetres across. If you went up from that, the smallest cobble at 60 millimetres would be much bigger. If you're in an auditorium, this could be the size of one of the walls. If you're sitting at a desk looking at a computer screen, this would be the size of your desk. Below the sand range, the coarsest end of the silt range, you can see a much smaller particle there. And below that again, I've illustrated a clay particle. Now that's actually bigger than it really would be. It's just the computer will only give me a minimum size of 1 pixel. And that's what we've got there. It's actually 1/30th of the diameter of the silt particle. Now we also need to talk a bit about the structure of the soils, how they fit together, and how they obtain their strength. In granular soils, talking sands, gravels, silts, things like road bases, they're a collection of individual particles which are supported by whatever point-to-point contacts they have between the particles. There's no cohesion between them, which means that they don't stick together. You'll see this, say, in a dry sand. Everyone's seen that on a beach. The particles just do not stick together at all. They'll run through your fingers individually. It's also why things like hourglasses work with sand in them. And the overall stability of a material like that depends on how the particles are packed together. So it covers both the range of sizes and their shapes, and how big the spaces are in between them. With clays, which are much finer, the situation is quite different. The mineral particles are generally in the form of flat plates, which I've tried very crudely to illustrate here. They generally form one of two structures. The first is called flocculated, where the particles are predominantly in an edge to face contact, so that you can see they're held apart. There are large spaces between them. But overall, the structure can work a bit like a sort of truss system, and it can be quite strong and fairly difficult to deform. However, it's got a lot of void space in it. So potentially, that could be reduced quite a lot. The other major structure is what's called a dispersed structure, where the same flat plates are more or less parallel. There's still a fair bit of void content in there, wherever they don't line up perfectly, but it's a lot more easy to move the particles around relative to one another, because they haven't got that sort of rigid truss arrangement. Now, if you can imagine this with some water in there, you can imagine this as a bit like plates of glass together. It's very easy to slide them around, very difficult to pull them apart. Now, I talked a bit earlier about the effect of grading and the way particles are packed together. If we start off by imagining a group of sand particles such as this, there's a limit to how closely they can be packed together. I've shown this as fairly loosely packed, and obviously you can think of some ways of putting those back a bit more close together, but regardless of how you do it, there's still going to be some fairly large voids between the particles, which there is no way of filling. Now if we had some smaller particles, we could pack those into those spaces, something like this. If we had some still smaller particles, we could pack those into the remaining voids, and you will see at this point that there's really no way of making that void space any smaller by packing the existing particles more closely. But if we had some smaller ones, they would fit in, something like this. And again, if we had yet smaller ones, we can fill part of the remaining voids. Now that can go on for some time. Obviously it could extend to larger particles and then down through the size ranges into much, much smaller particles. And obviously, as we continue with that process, you'll find that the overall strength of the material is increasing because there is more contact and more friction between the various particles, and the void content is decreasing because we're filling them progressively. That in fact is the reason why we have grading specifications for things like road base, is to ensure that increase in strength and reduction in void content. But that's really a topic for another day. Now, we need also to consider what happens to water when we place them in when we place it in a soil, something like that. Now, if the soil's dry, obviously what you have is a collection of particles which are just sitting there, and in this case I've illustrated them in a very loose structure. As water is added to a material like that, initially it distributes itself around the surface of the particles in a very thin layer, and conceptually it looks something like this. It's a fairly thin layer, it's fairly uniform, distributed right through the soil particles. What you'll also see in a case like that is where the particles are in close contact or almost in contact, you'll get a thicker layer held by surface tension around the interface. So something like that. Now, as we add more water, the water doesn't just go to fill the voids. What happens is those surface films become thicker, something like this. And for the purposes of this, we're only interested in the voids between the particles. We'll ignore the area around the outside of the diagram. As those films get thicker, the voids start to fill up, and rather than having perhaps an almost continuous network of voids, you have what amounts to small bubbles of air trapped in water-filled voids, and eventually, as you add more water, the soil becomes completely saturated. Now, in a case like that, if we know the density of the particles, we can work out the density of the soil at a given moisture content if we assume all the voids are filled with water. It's fairly easy. We know the density of the particles, we know the density of water equals 1. You can just work it out proportionally. And if you do that for a variety of moisture contents, you can establish a curve that looks something like this. It's known in our business as the zero air voids line or curve, and on that line a soil with a given particle density is saturated, and that means that you can't get any more water into it at all because all the voids are full of water already. So you can say on a graph like that that results above that curve are impossible. If you get a result there, it means either you've misunderstood the density of the particles or something has gone wrong in the test. Now, having worked that out, it's also very easy to work out what the density of the soil would be if it was only partly saturated. And say you had 2% of the voids, or 2% of the soil was actually full of air rather than water. So you could get curves like this at 2% and 5% air voids, as I've shown here. And equally, you can continue that sort of calculation for 10, 20 or 30% air voids if you wish to. Now we need to consider a little bit about what's happening during compaction. We mentioned the principles right at the beginning. To go back over it, the first thing that's happened is that we're packing the grains closer together. And generally that means the air is expelled because we're not dealing with a saturated soil, so we'll force air out rather than water. Secondly, the degree of saturation increases. The smaller voids start to fill with water. Again, that follows from what we've discussed. The amount of water isn't changing, the amount of air is. So the degree of saturation, which is really just the ratio of water to total voids, is increasing. What that results in is a local reduction in the strength of the material. Whenever a small void, as part of this, becomes filled with water, it transfers the loads that are imposed on it to all the other particles it's in contact with, rather than just to the next particle that is in physical contact with the one adjacent to it. And it makes it easier to move them around. Now, as you compact the soil, you get an increase in the degree of saturation. Those saturated voids become more common, and the loss of shear strength becomes more widespread. Eventually to the point where the soil starts to lose shear strength and the whole thing can move around rather easily under rolling. And some of you may have seen that happen. Now let's illustrate some of this. What happens? Here we have the diagram from before, partly saturated, some nice large voids. As I said at the time, it's a very loose structure, and it's not hard to imagine how that could be more compacted. So let's imagine that, and here we illustrate it. And here we have it definitely more compacted. Small air pockets right through it. It's still a fairly loose structure in this case, but it's close to saturation. And if you can imagine that actually being a box, that would be quite stable, provided the sides were supported, but also clearly if it were not supported, the slightest disturbance would cause that to become denser. Now, we can also imagine this with all the air gone, so it's now saturated. Now at that point, if we want to make it denser, there's no more air to squeeze out. So we can, but it comes at with the effect of squeezing some of the water out. Now in this case we have soil at its most dense condition, and what we see above it is the water that has to be squeezed out in order to achieve that compaction. Now in this case that is actually the highest density that you can get with single sized particles, close packed spheres, and they're packed together the same way as the billiard balls are or the snooker balls are in a frame at the start of a snooker match. There's just no way of getting them closer together. Now, some various ways of applying compaction. And again, most of you will be familiar with this, at least in principle, because you'll have seen most of these types of plant around. The simplest is just by applying static weight, say by a non-vibrating smooth drum roller, or by the old 3-point, what used to be called steamrollers. And that's all it is weight, nothing else. You can apply vibration, which obviously helps move the particles around and is particularly effective in non-cohesive materials like sands and to a large extent road bases. You can have dynamic compaction. It can be impact rollers, grid rollers. Generally not used in pavement, but are frequently used in some sorts of earthworks. Less so in roadworks, except for the grid roller, but on large landfills, impact rollers are becoming quite common these days. You can apply a kneading action, say by using a sheep's foot roller, or tamping foot. There's very many of those around. A pad foot roller used without vibration would also come into that category. More commonly these days, plant uses combined methods, say with a vibrating pad foot, where you've got two actions going on simultaneously, or via rubber-tired rollers, where you've got both static weight and a kneading action. The intention in those cases is to get the maximum benefit out of a single item of plant, so it can be used in several modes. Makes it more versatile, and also does several things at once to one material. But it's important to keep in mind that all we're doing is getting the particles to move relative to one another and to decrease the void space between them. The other thing I need to talk about at this stage is what I've called a compaction routine. Now, that's a fairly simple concept. It simply means one or more rollers, define the types, define their masses, define any variable settings that they may have. Depending on the type of roller, that would be things like vibration frequency or vibration amplitude, or say tyre pressure if it's a multi-tyre roller. Define the travel speed, which affects the amount of effort that's put onto each point of a compaction lot, and we define the number of passes over each point in the lot with that combination of rollers. Now, if you keep all those things constant, we have a routine. If they vary, we don't. That's really all there is to that. But when we come to talk about the principles involved, it's important to remember that a routine has to be constant. It can't keep changing. Now, suppose now we're out in the field and we've got a material to compact. We've got some rollers there. We've got an idea of how we intend to use them, so we've got a routine worked out. The only variable then we have is the material itself. Now, it's whatever it is. At that point, the only thing we can control about it is the moisture content. And let's just say it's as it's come out of whatever source it is. And the opinion of older and wiser heads is that it looks a bit dry. But nevertheless, we'll see what we get. So we apply our compaction routine. We can easily measure the moisture content. We can easily measure the density that we've achieved. If we do both those things, somewhere on a graph like that we'll have a point. Could be anywhere, but we'll have a point. Now, if we listen to the older and wiser heads, we may decide, well, let's see what we get if we increase the moisture content. We'll add maybe a couple of % of moisture. Do the whole thing again, exactly the same routine, do our measurements again, and we'll get another point. Now, if it really was drier than it should be, that point will be at a higher moisture content, must be because we've added water, and the density will also be higher, which proves the point. Perhaps it was drier than it needed to be. Now, having thought that's a good thing, let's do it again. So we do the same thing again, more water, go through the process again, we get a third point. And same effect, not as marked, but the density is still going up. We try it again. This time, the density didn't go up, it went down slightly. You think, maybe that was a fluke, let's try it again. So add more water, try it again, through the process, moisture, density, and we get a fifth point, and this one is quite definitely lower. Okay, so there's no point pursuing that. So what have we found? Well, in fact, we can draw a smooth curve through those, which is a compaction curve for that roller combination, that compaction routine, something like this. And from that, we can determine two things which apply to that routine and this material. The first is that there is a maximum density we can achieve in this material using that routine. The second thing is there is a very definite moisture content at which we will get that maximum density. That's the best moisture content for that routine, and we call that the optimum moisture content. Now, that applies to that compaction routine. And clearly we're not going to do any better using that routine. So the other option we have is to change it. Suppose we decide that we didn't achieve what we wanted, we need more compaction, we need more compactive effort. That seems the logical way to go. Now, we can construct a similar curve, which I won't go right through the details of, but at a higher compactive effort, it'll look something like this. We'll get more density, but we'll get it at a lower optimum moisture content. The best result will be at a lower moisture content than our initial efforts. If we go the other way, and let's just say we're extremely optimistic and we think we can get the result with a couple of passes of a tennis court roller, we'll also get a compaction curve. It will look something like this. It'll be flatter, it'll show a higher optimum moisture content and a lower maximum density. Now, this is where it gets interesting and ties back to the principles we were talking about earlier. Because if we put the appropriate air voids curves on here for the density of the particles, your graph will look like this. You'll find that the optimum moisture content, maximum density lies on something like the 5% air voids curve, and that the wet leg of those curves on the increasing moisture content side will start to run parallel to the 2% air voids curve. And that reflects the fact that it's for a given compactive effort, it's really difficult to squeeze, or for any compactive effort, it's really difficult to squeeze that last couple of percent of air out of it. So what you find is that you're filling the voids and overfilling the voids, but not getting the last bit of air out, and as a result the density is going down rather than up. Now that may be manifested in the field in various sorts of instability. The fill may start moving around, or you may get local shearing in it, but you won't really get beyond that point. Now, what does all this tell you? Firstly, there is a maximum density for any material that a given routine will give you. You won't do better. For that material and routine, there is an optimum moisture content which will give you that density. If you use any other moisture content, you'll get a lower density. To do better than that, the compaction routine has to change. Now the question is there an easier way than trial and error? Obviously, your foreman, for instance, or your manager, if you are the foreman, is not going to appreciate you spending all week playing with rollers to see what to do and then getting it wrong. So, is there an easier way? Well, the answer is yes, there is. That's where your friendly testing laboratory can come into the procedure for you. What can they do? Well, they have some laboratory tests which simulate what you do in the field. They use a drop hammer to do the compacting, so it's effectively a form of dynamic compaction. It uses fixed compactive efforts, just like a compaction routine, and it comes in two flavours. One is what's called standard compaction, which involves a smaller drop hammer, a smaller height, and a fixed number of blows. Or we have modified compaction, which is a much heavier effort, 4.5 times that for standard compaction. Now, both of those will provide maximum density and optimum moisture content results, and you can relate those to the field optimum that you might have for your rollers. Most typically, the modified compaction gives you something very close to field optimum. Standard compaction gives you generally between about 1% and 3% higher than field optimum, but it's not hard to work out the relationship. The big advantage to it is that it's much cheaper and much quicker. Now, when we do this, we can plot the results on the same sort of graph as we've already discussed, and you can get a variety of different curves. If you have a heavy clay, you'll have a relatively low density and a relatively high optimum moisture content. If you've got something like a clayey sand, which is, say, many naturally occurring selects, or if you're in Sydney, say, a lot of the sandstone materials, you'll have a higher density and a substantially lower optimum moisture content. If you've got a road base, you'll have higher density again and an even lower optimum. Now, the range is substantial. The range of optimum moisture contents can range from, say, 7 or 8% for a lot of crushed rock materials, up to perhaps 40% or above for some really heavy clays, and anywhere in between. If you go from standard compaction, as I've shown here, to modified compaction, say for a base material, you'll get the effect we described with increased compactive effort with rollers. The density will be higher, the optimum moisture content will be lower. Now, from that, and from similar results, we can actually deduce something important about this, what I've described as the law of diminishing returns in compaction. If we normalise results, say, by dividing them by the standard maximum density, we can see that at one end, and we call that 100%, we can see at one end modified compaction will perhaps give you about 5% higher density. It comes at the price of 4.5 times the compactive effort. We know that from laboratory testing we can get about 95% of standard compaction, and that requires perhaps 1/6 of the compactive effort. We also know that if you take the material and just spread it out on the road loose, it's got a relative compaction of somewhere in the low 80%. And we can draw a curve through that. And that shows very clearly that as you go for higher and higher densities, the effort involved will increase exponentially. And it really becomes very difficult to get much more. We'll come back to that, but it's important in understanding what we get from test results and what actually happens in the field when we see our compaction lots tested. Now, measuring compaction, I've talked about normalised compaction in a previous slide. We'd normally refer to it as relative compaction, and it's really just the field density divided by the laboratory maximum density as a percentage, so multiplied by 100. It can be done either wet or dry, that is with or without taking the moisture content into account, as long as it's done consistently. And it can be done at either standard or modified compaction as the laboratory density. Our specifications normally use standard compaction, but under some circumstances modified compaction may be used. In other areas, other states, modified compaction is more commonly used. We work out the compaction results not just for individual tests, but in terms of a characteristic value for a lot. Let's say an area of work which is supposed to be homogeneous. It's worked out from a fairly simple equation which looks a bit formidable. The characteristic value is Q, and it's really just the average for the lot minus a fraction of the standard deviation, which is just a measure of how variable the results are. The constant K varies with the number of tests, which depends on the size of the lot. And the intention of that is that the Q value will give you a result for which 85% of the lot is higher and about 15% is lower. The intention that none of it will be below a somewhat lower value, which is the minimum we need for design. And as I said, it's only valid if the lot's homogeneous. That's basic statistics. If they're not all of the same, if the results aren't all of the same type, then doing statistics on them is meaningless. Now, some implications for practice. We've got here two different sets of curves. The two at the bottom right are for a clay, say at standard compaction, and then above it to the left at modified compaction. The two on the upper left are for a road base under the same circumstances. Now, Considering the road base first, in that case we know our target is a Q of 102%. So that's more compaction than we can achieve with the standard compactive effort. And we can draw that on the graph fairly simply. It means that we're going to have to apply something like modified compaction, just for argument's sake, so a bit of effort. And if we look at the specified limit, it seems we have there a range of moisture contents using that effort which will give us the required level of compaction. Okay, not so bad so far. But in practice, to achieve that characteristic value, because it's at the bottom end of the range of values, the average has to be higher than that. So our target for compaction is going to have to be somewhere close to, just below, maximum density for modified compaction. And at that point, we've only got a very small range of moisture contents to work with. So that immediately tells us that we have to be very careful in both determining the moisture content we use for compaction in those types of materials and in making sure that it's very uniform. If it starts to spread out, you won't get uniform compaction and your lot will fail. If we go back to the clay material, the same principles apply even if we're going for a very high compaction standard, but we have a much greater range of moisture contents in which we can achieve it. And even if we allow for the higher target value, we've still got a much higher range. And again, this is consistent with what most people have seen in practice, that clay cohesive materials are a lot easier to get the compaction in than granular materials like pavements. Now, some practicalities. Typical problems that you may face during construction work, and anyone with any experience will have seen most of these at one time or another. Most common complaint, can't reach the specified compaction. Now that can mean uniformly you can't, or it can mean that the results are all over the place and that while you're mostly getting it, there's sufficient variation that the Q value doesn't come in. It can even happen that it's fairly uniform and some are extremely high, and that takes the Q value out even though no individual results have failed. That's a result of lack of uniformity. The material may be unstable under rolling. Common if it gets too wet. Local soft spots are appearing. Again, can be common if it's not uniform. Starting to see compaction-induced shearing. People may call a flake. Results from material being over-compacted in one part of the layer and under-compacted elsewhere. We'll look at that again a bit further on as well. You may see material starting to break down over rolling, particularly if you have to use very heavy compactive effort, or the lot's failing and it has to be recompacted more than once. In some materials that can break it down to an extreme extent. I have seen occasions in which that's gone to the point where the material had to be spoiled. It becomes so unworkable due to breakdown. And very commonly there is trouble with edges and interfaces. That can come for a variety of reasons. Now, some of the reasons for these, and I think you'll be able to deduce many of them, layer thicknesses are too great, so rollers just cannot reach the bottom of the layer, or they're irregular. You get variation in material properties through the lot. The extent of that depends on what you're doing. In some cases it's very uniform, but in others, particularly with earthworks or from a variable quarry source, it may be all over the place. The moisture condition may be wrong, either inappropriate in the sense that it's not sufficiently aligned to the field optimum for your compaction routine, or that it's too variable, so that say average is okay but it's all over the place. There are some points which are too wet and some which are too dry. You may have a problem in the underlying layers. and they're unstable. Now, that may be because of their inherent condition when you started to place material, or it may be, say, because they've got wet up either from water you've added or from rainfall, which has seeped down through the layer you're trying to compact and got into the underlying material. It's then trapped. It may be your compaction routine is inconsistent. That is unfortunately very common, either because the rollers aren't tracking properly, or because for some reason, maybe to do with construction traffic, they're just not covering every area. And that will give you variable results because the compactive effort is not the same, even if everything else is okay. It may be that you're using the wrong equipment, or the routine is just not optimum for your circumstances. In that case, something has to be changed. The point about these is all of these could happen in any material. They're not specifically related to a particular type of gravel or type of clay, anything like that. We've discussed uniformity. It's important for a variety of reasons, some of which we've touched on, to ensure that your lot is uniform. Now, let's consider, in the light of what we've heard so far, what happens with a uniform lot, and what are the effects of it not being uniform. Suppose this is material that you've placed today. It's at 80% of standard optimum, so very close to your field optimum for your rollers. All should go well, provided it's uniform. But suppose today was Monday, and that corner of the lot was placed a week ago in the middle of summer. It's a different material because it came from a different source, say at the other end of the fill. It's sandier, optimum is lower, it has been baked out in the sun for a week, so it's considerably drier. If your compaction routine's set up for the bulk of the lot, what's going to happen there? It's almost certainly not going to be the optimum routine for it. And even if it is, and you're lucky, the fact that it's so much drier means you won't get the same compaction. It will definitely come up short. Now, suppose there's another variation, the other end of the fill. You've come up with something clayey. It's also a bit drier, but you can see that as it comes out. It needs water added to it. Suppose you've done that. Okay, fine. You've got it to a similar condition to the bulk of the lot, and you're hoping your compaction routine will still work on it. But your water carts have sprayed over the edge of the clayey material, and you've now got a wet strip in there. What's going to happen now? Your compaction routine will give you an unstable area there along that strip, and it will start heaving. So instead of having a very simple uniform task, we've now got a mess. Some bits not compacted because they're different and too dry. Some bits not compacted because they're the same but too wet. Others, it's a different material, and maybe your compaction routine will work, or maybe it will not. You may be lucky, but in the long run, this will give you trouble. Now, some specific problems which relate to specific materials. There are a number of them which are commonly encountered. Highly organic soils, peat, muck, stuff you find in swamps. That generally gets spoiled because it's almost impossible to handle. Very difficult to compact, very difficult to keep compacted. Silts and sandy silts of some sorts are in the same boat, very difficult to handle because their compaction curve in the laboratory and in the field is extremely peaky, so you only have a very narrow range of moisture contents to work in. And it can be to the point where that range is so narrow it's not practical to achieve it. So the material is always either too wet or too dry. Clean sands, which are quite different in their behaviour from most gravels or most soils, and often have to be compacted almost bone dry or very close to saturation with vibration in order to get them down. Now, in that case, if anyone who's been to a beach and tried to build a sandcastle will understand the difference. Has to do with the resistance of the material to compaction and to its shear strength. On a beach, you'll see that dry sand has got very little shear strength. You can't build a sandcastle out of it. You can if you compact it enough, but in practice you can't. Wet sand also you can't build a sandcastle out of. It just flows. In fact, they both flow. If you want a sandcastle, you've got to have an intermediate moisture content. You can stack that up vertically, cut vertical surfaces in it while it retains that dampness. That means it's got a lot of internal strength derived from the water films inside it and their surface tension. It also makes it very difficult to compact it very densely using any method, vibration, static, anything. So that requires a special technique. Bony gravels are much in the same sort of class and are often afflicted by poor shape as well. And finally, macadams and rockfills are in a class of their own. You can't laboratory test them the way we've been discussing for soils, and you have to work them out in the field. Often you have to have a very specific attempt to develop an appropriate compaction routine. Again, we'll discuss that a bit later. Now, all of those issues relate to the specific type of material and will only be found in those types, not in general materials. Now, supposing you're having trouble achieving compaction, what are the appropriate strategies? And there's a few, more or less in order of increasing difficulty and cost. The most common is just do some more rolling. Second is rip it up and try it again, reworking it. That may be accompanied by changing the moisture condition, reconditioning it. That can be either wetting or drying. We can try modifying the compaction routine, so different rollers, different sequence, different number of passes. We can try modifying the material if it's really resistant. That can mean blending it with something else. It can mean chemical modification. Starting to become expensive at this point. We can remove it and replace it. If it's really intractable, that may be the only way out of it. And if all else fails, we can try bridging it or some other form of working platform, say by chemical stabilisation, which drastically increases its strength to the point where you can get away with not having it compacted. Generally only works fairly well down in the formation. It's not a good idea near the pavement unless you've got no choice. Now, some things that usually don't work, again based on many years of bitter experience. If you've compacted the material, you're not going to have much joy just trying to get water into it by spraying on the top. It's hard to get it to soak in, and if it does, it's never evenly distributed. So it will either be hung up on in the top of the material, or it will go straight to the bottom, the usual alternatives. Just keep going with the rolling when it's obviously too dry, and sometimes people do it when it's obviously too wet. It generally won't work. We've seen why. As you get away from optimum moisture content, it just gets harder and harder. If you do continue rolling when it's too dry, particularly, you'll find yourself way out on the right-hand side of that diminishing returns curve that we looked at earlier. Much effort, very little return. If the layers become unstable or it's started to shear below the surface, whether it's locally or it's widespread, it's very difficult to succeed in trying to roll it out. It won't work at all if it's sheared, and it's unlikely to work if it's unstable. You really have to wait for it to dry out in that case. If you've got a problem in the underlying layers, you will not solve it from the top. You'll have to dig it out or wait. Depends on how much time you've got. Waiting can be a very long process. Best to make sure it doesn't happen in the first place. If you've got a moisture susceptible material underneath the layer you're trying to compact, flooding water into it is not an appropriate solution. It will get into the underlying material and cause it to become unstable. And finally, burying mistakes. It's often the pragmatic solution, particularly adopted by those who don't have to live with the consequences later on. But the problem always comes back to bite us in the long run. It's not a good idea. There will be times when, best efforts of man and beast, it is necessary to start from scratch using your rollers out in the field to find out what's the best way of compacting a given material. Going back to the idea we started with when we were talking about compaction curves. Now, there's many ways of going about that, but there's some principles that should be kept in mind at all times when you're doing it. The first is be systematic and only change one thing at a time. Then you'll find out how the thing you've changed affects your compaction. If you change everything, even if you fluke it, you'll never know exactly what you did and how much changing something else small could affect your field results. Leads to much mystification and much wasted time. So the way I would start doing it is firstly prepare a uniform pad, uniform material, uniform moisture content. Best to start at your best estimate for field optimum moisture content or just above. You often will be able to guess that or estimate it from your laboratory results or from past experience with that type of roller. Where you start depends on the weather. If it's going to be hot and dry, start above. If it's going to be cool and humid, start at field optimum, not above, which will be waiting a long time for it to dry out if it's too high. Use your selected starting roller first. Find the optimum routine for that. In fact, you'll go past the point of diminishing returns with that roller, and then you'll work out what the optimum number of passes is, and perhaps what the settings are for it. You may need to do separate trials to optimize the settings. Then prepare another pad using that first roller with its best routine, and start again using the next roller you plan to use. Obviously, normally there would only be perhaps 2 rollers. Under some circumstances there may be 3 or 4. What you'd expect to see is something like this. If you can imagine your compaction lot in cross-section, so you've cut a slot through it, and no passes, it obviously will look loose but very uniform. As you do the first couple of passes, and that's really up and back from one end, you'll see it's compacted significantly. The total length of this may only need to be 20 or 30 metres, so that each couple of passes goes a few metres less towards one end, and so you can work out what density you've obtained for each successive pair of passes. It will be pairs because you've got to go up and back each time. After 4 passes it might look something like this, after 6 it might look like that, and after 8 it might look like that. The thing you'll see is that you're getting less additional compaction for each pair of passes. In fact, that looks very much like the diminishing returns curve turned upside down, and in fact that's exactly what it is. From that, and from measuring the density, you'll be assuming the material is uniform. You'll get a pretty good idea of when you should stop with that roller. Now, a brief word on specification requirements, which is after all the target we're trying to achieve in our compaction. And there's quite a few things there, and from what we've seen so far you may be able to better understand what the reason for them is. Firstly, we ask for uniformity for each production lot. That applies to materials as far as possible. The criticality of that depends on what it is. It's less critical for general earthworks than it is for select, and more critical again for pavement. And we're asking for uniformity in the compaction process. There are grading requirements for earth fill and for rock fill. One requires, the earth fill has a strict restriction on the amount of coarse material. It's over 37.5 millimetres that it can contain. Rock fill has a strict requirement on the amount of fines that can be incorporated in it. And there is a strict ban on materials intermediate between those, which we've called hybrid fills. The reason is they are very difficult to compact properly, and they are very difficult, in fact impossible, to test adequately. So there's no way of confirming whether the appropriate compaction's been achieved or not. There are restrictions on layer thickness. Generally 300 millimetres for general earthworks. That can increase to 500 millimetres if there's a lot of coarse rock, but it gives you a problem in testing it if you do that, simply because the standard techniques using nuclear meters don't reach down that far. For select materials and pavement, it's usually 150 millimetres maximum. Under some circumstances that may be less or it may be more. I've seen it up to 175 in a single lift. It can get difficult to compact beyond that. Throughout, there's a maximum particle size restriction of 2/3 of the layer thickness, and that's to stop materials bridging across the layer, so that when the roller goes over, the load's transmitted straight through the particle into the underlying material and doesn't compact the layer that you're trying to compact. And there are restrictions on moisture content. That's at the time of compaction, not at the time of testing, which is a bit of a trap for young players. If it's been baking in the sun for 2 days, the moisture content is not going to be what it was at the time of compaction. And there's a range of 60 to 90% of standard optimum required. And that is really to stop attempts to compact the material well above the roller optimum and the subsequent instability problems, or to compact it too dry, which usually results in a lot of wasted effort and encourages material breakdown. We should add to that it's not a statistical requirement. It applies to each individual point, and if you think about the way that statistics are worked out, characteristic values there would be quite misleading. There is a requirement that compaction be uniform over the full area and depth of each lot. That makes sense. We want it to be the same. There is a characteristic value requirement for compaction. We've discussed the basis of that a bit earlier. It varies with the nature of the material and its position in the formation. Generally, the requirement gets higher as we go up, as strength requirements amounting to shear strength and load carrying capacity increase, and most critical in the upper parts and in the pavement. There are provisions for proof rolling. They can apply to any layer, and the material must be stable under proof rolling. They're not compulsory for every layer, but they will be used particularly if the material tests up as being wetter than it should be. And there are requirements for deflection testing at the upper and lower surfaces of the select layer, and that's effectively a calibrated form of proof rolling, and it's intended to ensure uniformity of support for the pavement once it's placed on top of the select. There is also a specification for rock fill. Compaction there is quite different because it can't be tested simply. So it's required to develop a method specification. It means you've got to develop a suitable compaction routine from scratch, and that will depend on the grading of the material and the rollers that you've got available and the layer thicknesses. It applies to rock fill, it applies to capping layers in rock fill, and it applies to drainage blankets, the latter of which is probably the most common application these days. As I've said, you need to develop a suitable routine. It's got to produce satisfactory trial sections, at least 2, and it must be able to withstand proof rolling. Now, a related question, we've discussed specification requirements. We often see numbers for relative compaction. Some of those look very impressive, some look marginal, some look poor. It's important to know what is really possible in compaction. Now, we've discussed the factors that control this. There are quite a number. Some of them are inherent to the material. They include the grading, particle shape, and the cohesiveness of the material. Grading affects both packing and shear strength. Particle shape affects the way the material packs together. Cohesion relates to the clay content and also affects the ease with which the material can be compacted at a given moisture content. And then there are operational variables which are under your control. They include moisture content, the compaction equipment and routines that you can use. Clearly you've got control of that. And the layer thickness. Now that one is fairly important. I can illustrate why based on some evidence that we've obtained recently in attempting to compact a select layer in a 300mm single lift, all from the top. Now this was tested in detail to determine whether we were obtaining the full compaction through the layer, which was the point we were concerned about. And what we have found can be illustrated on this graph. The densities were determined by difference using a nuclear meter at 25mm intervals, then averaged through the lot. The zigzag line that you can see on this graph represents the averages for each lift. And as you can see, it's a bit of a sawtooth, but appears to be going down to the right-hand end, which is greater depth. The red line is a little bit of elementary curve smoothing, and you can see from that we've obtained very good densities, probably down to about 200mm or just below, just above, and below that the achieved density starts to fall off fairly rapidly. And to give you an idea of where we are, the highest part of that curve between about 75 and 175mm is equivalent to about 107% of standard compaction. Drops to about 95% at the right hand end and is clearly heading south fairly rapidly. Now, we can discuss briefly some limits to what is actually physically possible based on the testing. The blue hatched area there is our standard moisture content range within which you're allowed to compact. We've shown the standard optimum moisture content and maximum density as 100%. Within the range that we're allowed to compact, and that'll be using something like modified compaction, there's a range of possibilities depending on how well it's compacted. Really, you're not going to get beyond that 2% air voids line. You'll be a bit to the left of it, and you're certainly not going to achieve more than perhaps 108, 110% with any reasonable compactive effort. It's just not physically possible. In theory, you could end up with a point like the one up at the top left, but to achieve it, firstly, you'd have compaction shears all through the thing, and secondly, you'd have an enormous compactive effort. It's a warning, just from the basic theory of this, about what is really achievable and what you should be looking for when evaluating results that you see. Because we sometimes, and with increasing frequency, are seeing some very high apparent compaction results. Now, what should you look for? In granular materials such as road bases, most select, really relative compactions bigger than about 106% is very unlikely. It can happen, if only because of experimental error in individual results, but really as a systematic thing it's unlikely. Results above about 108% are practically almost impossible and should be treated with vast suspicion. For more cohesive materials, it's a similar story, but because there are more voids in there to begin with, and a greater range of moisture contents you can work in, you can achieve a bit more. In that case, 108% is unlikely and 110% is almost impossible. And in this case, we're talking about individual results, not the characteristic values. Realistic characteristic values would be 1% or 2 lower than those. And the other thing to watch out for is that if you're getting extremely variable compaction results in a lot that appears uniform, there is something wrong, and it is most likely with the results. Now, if we graph some results up on the type of graph we've been looking at through this presentation, this is what fairly consistent results might look like. The laboratory compaction results, which are the circles, in this case are all neatly grouped along the 5% air voids line. The field compaction results are a bit up and a bit to the left. Now in this case, this one would not reach the Q value because you've got one low value there, but the results all look feasible. When you actually plot them, the place they fall on relative to those air voids lines will vary because the density of the particles may vary, but the trend should be parallel to them, particularly for the laboratory results. In other cases, you may get something quite different. Unfortunately, these are all based on actual cases. Here we can see the laboratory results all show about the same optimum, but there's a huge scatter in the maximum densities. The field results perhaps look reasonable, although there is a bit of a scatter, but there's at least one set which is obviously a quite different material because the values are far over to the right, and the field result associated with it is just plain impossible. And there is no way you can move the voids curves around on that diagram to make both of those results look feasible. Either the laboratory result is very low or the field result is very high, or both. So this type of graph shows you where a real problem exists, and it must relate in this case to the testing. In another case, we've got similarly erratic results trailing off more or less in a horizontal line to the left, and we see laboratory results where the laboratory densities are more or less constant, but the optimum moisture content varies over a range of about 6%. Again, this is not particularly feasible. We think back to what we saw as consistent results. They're much more tightly grouped and on the 5% air voids line. So what do these results mean? The major thing is there is a problem with either the sampling or the testing or both. If you're starting to see particularly very high relative compaction results, that is almost certain. The real concern is that's only a symptom. It doesn't just apply to the isolated results. There is something causing it, and it's unlikely to be confined just to the ones which give you high results, particularly if it relates to the laboratory standard density figures. Your real question is, if you're getting 115% and it really should be 105%, what does a report at 102 or 98 mean? Should that be 92 or 88? Even if it's not that bad. It can indicate that much of your compaction which purports to pass specification requirements is really failing. And that matters because it's strongly associated with poor long-term performance. So what can go wrong in all this to cause such problems? Field densities, which are mostly by the nuclear meter, which is the RTA test method T173. Low results usually are an operational problem in seating the gauge. That's by far the most common cause, but strangely we don't often see that. High results are much more common, and that often results from poor sampling practice. If the gauge is used properly, it's very hard to get a bad result, an invalid result out of it, but the moisture content that goes with it is very subject to sampling. The most common thing is for people to take samples only out of the top part of the layer, particularly if it's had a water card over it recently, so that the moisture content appears much higher than it really is for the whole layer. Where you get erratic results, which unfortunately is also common, it can be either of the above, but not consistently. It can be transcription or reading errors, or a mistake intermittently in a procedure. It can be a calibration problem, or erratic operation of the equipment. Or people have not taken counts of the background radiation where it's required, most commonly in trenches or near pipes, where readings should be taken at each test location. What else can go wrong? In the reference density, in this case, low results are the most common, and that results from the fact that most things you can do wrong in the test give you a low result. Again, poor sampling practice, not sampling through the full depth of a layer. Often materials are segregated within a layer, particularly if there's oversize present, and that results in an unrepresentative reference sample. Oversize may not be handled correctly. Most commonly, oversize discarded or not weighed properly when it should be included. It usually, in fact always, has a higher density than the overall material it occurs in, because it's usually, in fact always, rock, and always denser. Again, there can be weighing or transcription errors. There can be a lack of curing, which means that in the test there isn't sufficient time for added water to penetrate right through the material. And that gives you funny low results. High results are very rare and almost always the result of an error during, as in a mistake, during the conduct of the test. And finally, erratic results in that case can be any or all of the above, or they can be due to specific equipment problems. Has been noted to happen, for instance, in automatic compaction gear, and it needs to be checked regularly to make sure that they're functioning correctly.